There's actually cognitive bias research that has proven that judges rule more strictly when they, just before lunch when they're hungry, and they rule more leniently after they've been fed. So I have to take that into account and not prevail too long on your stomachs. So we all know that historians can't do without periodization. And one of the distinctive things about big history is periodization in terms of using emergent complexity. And this is a very familiar image we know from David Christians, or somebody else called it the Bill Gates version of big history at 8 levels of thresholds of emergent complexity. There's another very big picture periodization that I like to sometimes use. This is from Adam and Laughlin's 5 Ages of the Universe, where they divide the universe, the whole cosmology, into 5 periods. And so we have the primordial era, primarily dominated by radiation, and when matter forms, and we get the Stelliferous era that is dominated by stars and galaxies, and that matter comes together. We have the degenerate era that is dominated by the remains of stars. The black hole era dominated by black holes, and the dark era as the universe converges on thermodynamic equilibrium. Obviously, the science on this is not entirely certain, because the more we learn about cosmology, extrapolating into the far future is a dicey proposition, but it at least gives us a framework to think about far future cosmology and our place in the universe. So when we compare these two periodizations, we see that the big history periodization takes up a tiny little chunk of the 5 Ages of the Universe periodization, and this is a logarithmic scale on the bottom, so each of these is going up by each little division represents 10 times more time than the period before it. So we are going to focus on the Stelliferous era and what kind of emergent complexity we expect to see in the Stelliferous era. The Stelliferous era is typified by stars that engage in nucleosynthesis in their cores, creating heavier elements, and when the really big stars explode, they create even more elements. The Stelliferous era goes from about 1 million years from the Big Bang to 10 quadrillion years. Obviously, that's when the last of the stars will burn out, and that's not known. And it's also characterized by, the Stelliferous era is characterized by galactic ecology, the circulation of dust and gas, and there's also circulations within each of the galaxies of the dust and gas. There's also expansion of the universe that result in gravitationally bound structures eventually becoming isolated as other gravitationally bound structures move outside the cosmological horizon. Sorry about that. So the Stelliferous era is also typified by a lot of water. The most water that has been observed in the universe is at 12 billion light years away in the Lynx constellation. We've also detected a lot of astrochemistry in deep space, polyatomic organic molecules, including polycyclic aromatic hydrocarbons. There's a lot of literature on that if you care to look into it, but we know that there are a lot of basic organic molecules that exist on interstellar and intergalactic distances. And the polycyclic aromatic hydrocarbons interest us because they're the basis of the carbon chemistry of life. In a protostellar disk, protoplanetary disk around a forming star, tend to concentrate in areas which roughly correspond to the circumstellar habitable zone outside the soot line and inside the frost line, beyond which large gas giants tend to form. So, some terrestrial emergent complexities that have emerged on Earth from chemical and mineralogical complexity. We all know that life grows central nervous systems, which gives you sensations. In some animals, sensation has grown up into consciousness. In many species, you use tools, there's technology, there's also art, agricultural civilization, industrial civilization. I don't regard this list as definitive. It's just something I threw together. I realized later I should have included language in this as it significantly modifies consciousness. The kind of terrestrial emergent complexities we see are typified by what I call planetary endemism because it emerges on the surface of a planet. Surfaces of planets are wonderful places for interesting chemistry to take place because you've got energy flows driven by stellar insolation. You have interfaces between land surfaces, atmospheres, and liquid bodies. In each of those interfaces, you have a different kind of chemistry, and many of those different interfaces correspond to different theories of the origins of life. So the hydrothermal vent theory is the interface between the geosphere and the hydrosphere, and so on. You get the picture. There are a large number of geochemical processes on complex planets like Earth, like the phosphorus cycle, the nitrogen cycle, the sulfur cycle, and the carbon cycle. Each of these drive greater mineralogical and chemical compound complexities on planetary surfaces. But planetary endemism entails that emergent complexities that emerge as a result of all these interesting chemistry on planetary surfaces find themselves at the bottom of a gravity well. So, returning to the David Christian / Bill Gates 8 thresholds of emergent complexity, we see that the Big Bang formation of stars, heavier elements forming, and complex planet forming, these are things that we can observe over cosmological distances, whereas the rest of the emergent complexities from life on Earth and the things that are built up on life are only observed locally on the Earth. So what I'm suggesting is that we should be looking for peer emergent complexities, other emergent complexities that are, in a sense, on a par with us because they come from the same common ancestors. They branch off from the astrochemistry that we know is pervasive in the universe, because we can observe that all over. We can't observe the other forms of emergent complexity that are built up locally from the astrochemical chemistry and the chemistry on the surface of Earth. It may happen elsewhere, but it may happen differently elsewhere. So I want to contrast what I call a narrow peer emergent complexity class and a broad peer emergent complexity class. And this first item here is something I could devote a whole talk to, but I'm just going to say very briefly. Civilization is the missing piece of the SETI puzzle. SETI astronomers and scientists are looking essentially for techno-signatures that would have to be generated by a civilization, but there's no theory of civilization to describe exactly what it is that's being searched for. And we could use that. Narrowly conceived peers are indistinguishable as cosmological scales of magnification. So as when you see human figures from a distance, you can't tell them apart. You know they're all human beings, you know they're individuals, but when you view them from a distance, as we're viewing other exoplanets and other technosignatures and biosignatures, you don't see that individuality that you see is the large-scale similarities. And there is a scale of magnification close up at which you can distinguish these indistinguishable peers, but we're talking about the levels of cosmological visibility when we're talking about biosignatures and technosignatures. So what I'm suggesting also is that post-astrochemical peers, that is to say, peer emergent complexities that take astrochemistry as their common ancestor, may appear identical at low levels of resolution that you experience over cosmological distances. So, what I'm going to say is that a wide peer emergent complexity class, things that could be mistaken for each other at cosmological distances, they might not be civilizations, they might not be technological civilization, they might not be life, they might not be consciousness, but they would branch away from the astrochemical point of origin. They would serve as a point for further emergence in the same way that life on Earth has built up to civilization. They would exhibit planetary scale behavior if they conform to the planetary endemism thesis, which is to say that most emergent complexity is going to happen on the surface of planets because that's where the interesting chemistry takes place. And planetary system scale behavior if they happen to be an outlier that is not exemplifying planetary animism. And they will produce detectable signatures over interstellar distances. So from an anthropocentric perspective, which is our perspective, we see this tree of emergence that starts with life on Earth, and then we think about possible alternatives, which are called biochemical peers. Think of sensation, and that implies possibly sentient peers, consciousness, conscious peers, so on through the other items that I put on my earlier list here. Each of these can branch off into alternative possibilities on other worlds. But if we take the point of view from a common ancestor of astrochemistry, we see we might build up entirely different structures, and it's only at the base of this pyramid where life as we know it then branches off from the other astrochemical peers, and then other complexities get built on those alternative astrochemical peers that we might find elsewhere in the universe. So, going searching for more out-of-the-way conceptions of emergent complexity, one of the best explored conceptual space is the idea of alternative forms of life. So there's a lot of literature on that. Abraham Loeb has written a lot of interesting papers, and his paper talks about life in the very earliest origins of the universe, when things are warm enough that you could actually have life without having planets or planets as we know them today. And there's a whole tradition of papers on atmospheric habitable zones. This was brought to attention in the 70s by Carl Sagan, and there's been a couple of recent papers here I've cited that take that on. And obviously, if you have a kind of life that emerges in an atmospheric habitable zone, it's not going to develop in the way that our life on the surface first has developed. They're not going to have access to metals or anything like that. They're not going to be building any technological civilization. But other forms of emergent complexity might ultimately supervene on them. Also, reaching further afield, like yesterday we had Clement Vidal telling us about Stelliferous, which could be a really radically different form of emergent complexity, a very high energy density rate. Clement confirmed for me yesterday that he was aware of John Smart's transcension hypothesis. I noticed a similarity of that. So you can think of these as developments from a technological civilization that chose to evolve in the direction where it could assimilate vast amounts of energy, but you could also have very high energy density rates that came about through other processes that aren't exemplified in Earth or our solar system. And another, offbeat conception is the early 20th century work of Stelliferous, who wrote about the possibility of what he called crystalline life. So I want to, just as a thought experiment, talk about a scenario for pure emergent complexity as different as possible from what we know as emergent complexity on Earth, Because without life, without consciousness, without intelligence, without technology, without civilization. But I want to mention a couple of recent interesting papers that influenced my thinking in this regard. This is a Hamada paper that came out a few months, came out a few months ago, where this laboratory produced some very interesting artificial metabolism. It's not life, it's not a self-replicating macromolecule like DNA, but they've done some very interesting things. It shows the possibilities for chemical metabolism that aren't life, and we don't know how many variations on a theme there are. And then there's this other paper by Bialy and Loeb that caused a real ruckus last fall when they suggested that the Oumuamua might be an artificial interstellar probe. But if you read the fine print in the paper, they suggest here that it could be an artificial material, which they focus on, but it could be a natural material as well that is unknown. So building on those two ideas, my thought experiment in pure emergent complexity, you take a non-biological metabolism that emerges from, say, the chemical complexity of comets. If you have a solar system, a planetary system with comet swarms, which were once proposed as the explanation for the dimming of Voyagian star. So there's a lot of interesting chemistry in common tails. And if you get selection pressure on that emergent complexity for locomotion by means of membranes catching the solar wind, they could spread around their planetary system. And if you have a astrochemical equivalent of bioelectricity, like we have in eels or electroreceptions in sharks, they could even coordinate their system-wide activity within their system by radio signals. And by suggesting this bizarre possibility for emergent complexity that's not life, not conscious, not civilization, without technology, I'm not trying to suggest something that's really unusual. Actually, I'm trying to suggest something that exemplifies the principle of mediocrity. But I'm using the principle of mediocrity here in the sense of what I called earlier a wide peer conception, where over cosmological distances, these things wouldn't appear that different, because they would have, like I said, planetary scale activities. They would be visible by something like biosignatures or technosignatures over interstellar distances. And so once we start thinking about a broad peer concept for astrochemical peers, other things sort of like us, but not really like us, we could probably divide them up into classes, and they would probably, in terms of their frequency, define a bell curve. But first I want to talk about, to give you a sense of what I mean by wide peer class, I want to talk about peer mammalian intelligence. Now we think of we think of mammals as, there's a very big distribution in mammal intelligence from marsupials that aren't very smart, frankly, up through widely represented rodent species, cetaceans and primates with the pretty good encephalization quotient, and human beings, which are an outlier, but still the average mammal is smarter than the average reptile, and the average reptile is probably smarter than the average fish. So there's a peer mammalian intelligence, even though it covers a very, very broad spectrum. So I want to suggest the same thing with emergent complexities that have astrochemistry as their common ancestor. Who knows where we lie on this graph? We know we're not a universe spanning emergent complexity, though that might lie in the future if we do develop a spacefaring civilization and we spread and leave clues of ourselves throughout the universe. It doesn't seem likely that we're an average emergent complexity, because if this was the most widely, if technological civilizations like Earth were the most widely represented emergent complexity in the universe, we would have heard from them by now. This is a conceptual space that still needs to be filled. And that's one of the things I want to say is we need to, the idea of alternative forms of life is not, we still have to do a lot more work in terms of exploring, but we also need to explore scenarios of emergent complexity, alternative emergent complexity, or what I call peer emergent complexity, that lies within that wide class, and populate it with every possible variation on a theme, and to try to get a sense of our place within the other emergent complexities during the Stelliferous era that are our peers. So to relate this to SETI, a recent paper by Lingham and Loeb talks about the distinction between biosignatures and technosignatures. The final sentence here, the possibility that the boundaries between technosignatures and biosignatures could become blurred must be borne in mind. And then another paper that came out just after that, responding to it, from Cherkovich et al. We have fully accepted the tacit premise of the LL18, that was the Lingham and Loeb paper, that biosignatures are clearly and unambiguously distinguishable from technosignatures. One interesting speculative possibility that deserves more attention is that the distinction between biological technosignatures might eventually be erased. So what I'm suggesting is this is a future development in which it would be erased, but if you go back to think from starting from astrochemical peers and the way that branching bush of emergent complexity and developmental sequences may run differently, in other words, rewinding the tape of life, but rewinding it to before life, to astrochemistry, There's no reason to believe that it will be clearly able to distinguish between technosignatures and biosignatures. Take my earlier weird thought experiment of something that's not alive, but it's traveling on solar system scales and communicating and coordinating its activities through radio signals. If we receive those radio signals, would we even be able to interpret them? It might not be grammatical language, but it would be communication, it would be signaling, and we might, with sufficiently sensitive instruments, be able to detect that and to puzzle over it and not really know what it is. So when we take into mind what I've just suggested about astrochemical peers and a broad peer group, on the one hand, this allows us to formulate an even stronger version of the Fermi paradox, where not only have we not been visited or not heard from other civilizations, we haven't heard from peer emergent complexities that are not civilization that nevertheless have a cosmological presence. So that makes it even stronger and even weirder and harder to understand. On the other hand, we could be experiencing or seeing things that indicate alternative emergent complexities that are our peers, but we're completely incapable of interpreting them. So it's suggesting it was reasonable when Kardashev first suggested that the early quasars, before people knew what quasars were, might be modulated signals. When the first pulsar was discovered, it was thought it might be called LGM for little green men. It might be, we have reason, we know what pulsars and quasars now, but now we have the puzzle of fast radio bursts. Are they naturally produced, or are they technosignatures? We don't know, but what I'm suggesting is we don't necessarily have to choose, but we do need more information. So, grazie mille.
Two things. In an earlier talk, David Christian was quoted as saying that complexity emerges as great difficulty. I don't see the justification that was supported from the life of Earth very early in Earth history. Second, you said that we should have learned with ourselves already if we're at the peak. Primitive civilizations don't last long, and so it's not that we heard from Corti as well that, well, maybe it's another paper, that once that that is your paper, that we pass the window of being able to detect these photons. So there's a low population in the galaxy. Why would we inherit from primitive civilization? We don't even have the technology to detect these radiation from the whole galaxy.
To take your second remark first, if technological civilizations really were widely represented, we now have reason to believe there are a lot of Earth-like planets even within 50 light years of where we're at, or close enough. We're not talking about the other side of the galaxy. We're talking about tens of light years away. We're talking about easily a billion, 10 billion, 2 billion years of cosmological history that have been population 1 stars with planetary formation that probably included heavier minerals, so they could have had a technological civilization. Obviously, there are differing interpretations of the Fermi paradox. Some people just dismiss it and say, if you really look at it carefully, it's not a paradox. Other people say, well, this is the one thing you can't overcome. I think it needs to be studied more. I don't think that there's a basis for a consensus at the present time. But that's why I'm suggesting what I'm suggesting, that we need to think about it differently in terms of peers that have astrochemistry as the common ancestors, not this particular developmental sequence of emergent complexities we only see on Earth. So if you dismiss the possibilities of other civilizations being detected at tens of light years away, we just have to agree to disagree on that. But that's another conversation for another time after people's stomachs have been satisfied. I would have the difficulty understanding, hearing what you said, but you mentioned the David Christian quote in an earlier presentation of emergent complexity appears with difficulty. I think we really need more work on the idea of emergent complexity. Philosophers openly call it a term of art because it's very easy to be a hand-waving solution to a problem rather than a detailed solution to a problem that it obeys the canons of scientific explanation. But it's still, it's a point of departure. It's not, you're not finished when you say something's an emergent. So in terms of this particular problem here, we don't know when the Goldilocks conditions are present for emergence. We don't know if it's inevitable or not that they will emerge. And if they are inevitable, is there one kind? If you do emergent complexity, and this is really relevant to what I was saying earlier about astrochemical peers, how tightly constrained is emergence? We don't know. Can astrochemical peers only develop in the direction of the greater complexity of the self-replicating macromolecules that we call DNA or something so similar to it that you take the 4 bases and you replace one with another and you just get something that's just slightly different. So we don't know how tightly constrained emergent complexity is. If it's extremely tightly constrained, then the developmental sequence we've seen on Earth is the only developmental sequence that's possible. And if we're going to find anything that's interesting in the universe other than astrochemistry, it's going to be like us. If, on the other hand, emergence is not tightly constrained, which is why I cited the Hamada et al. Paper, is that there might be other forms of chemistry that give rise to other forms of complexity, and then they build a different developmental sequence, one on top of the other, that's radically different from what we have, which is why I suggested the thought experiment. Does that address at least in part what you said?
Well, in other words, they were Christians.
I can't hear you. Shout or no, I should.
Statement, not very difficult, it is problematic.
I agree it's problematic.
Okay, we agree.
One more question, please.
Yeah, thank you very much for the presentation. Super fast that was actually. So you said something about meteorite in one of the slides. I don't know whether you're suggesting that life was or began within a meteorite, or are you suggesting life was on its surface, or did I simply misunderstood? There was something about meteorite that you run through quickly. If you go first two, I think those two probabilities are not possible. So do you know what I'm talking about? There was some...
Could you repeat a little louder what those 2 possibilities were?
Okay. Right. In one of your slides, there was something about meteorite. I tried to read what you're saying about meteorite. Either you could have been suggesting that the life began within a meteorite and therefore delivered onto Earth, or else you're suggesting that life was made on its surface or elsewhere and delivered to Earth. Or the third possibility, I completely misunderstood what the bullet point was. So if you're suggesting the first 2 possibilities, I would put it to you that it's not probabilistic, either one of them. That is like within a meteorite, life on the surface of meteorite.
I agree with you that that is not particularly probabilistic, but I would also say and emphasize, I don't think that these scenarios are mutually exclusive. And in terms of improbable events, when you've got a universe as large as ours and as old as ours, that improbable events will happen. You know, if we are the only technological civilization, our presence here in Milan today is improbable, about as improbable as you can conceive of. So I would suggest that I wanted to emphasize that planetary surfaces are particularly good places for interesting chemistry because you've got the energy flows, you've got the geological processes, the water cycles, all of these are making more complex minerals than you find out in space, but still we do find interesting chemistry in space, we find interesting chemistry in comet tails, probably not on the surface of a meteorite, but there might be interesting planetary systems out there with different conditions where there is interesting chemistry on meteorite surfaces. But I'm not committed to the idea, and I don't think my argument stands or falls on that. Also, I don't think they're mutually exclusive.
Thank you to our presenters.